In this video, we are going to show a simple way to derive the Lorentz transformation by considering the path of a light beam in two inertial frames, moving with a constant velocity with respect to each other, and using only Einstein's two postulates of relativity. We will first consider a simple Galilean transformation in a Newtonian world, and then show how we need to apply the Lorentz transformation to avoid conflicts with Einstein's postulates. Simple mathematics derives the equations of special relativity. But first, we go back to where this all started. In the late 17th century, Isaac Newton developed a set of equations that would change the world. They elegantly described everyday occurrences, from the flight of a cannonball to the motion of the planets. The beauty of them is also in how they allow all observers to explain the world and events that take place in it in an identical way. Whilst one observer sees an apple falling whilst another sees the moon moving, the laws of physics explain all of their motions in the same way. Newton considered space and time to be equivalent for all observers, as seen in the quote from his famous Principia: "Absolute, true and mathematical time, of itself and by its own true nature, flows uniformly on, without regard to anything external."
Enter Albert Einstein, a patent clerk turned genius in 1905, who was attempting to solve the mystery of how a light behaves in different frames of reference. To achieve this, he thought about what would happen if he chased a beam of light whilst travelling at the same speed, and concluded that he would observe light acting like an electromagnetic wave. He came up with two postulates. First, the laws of physics are the same in all inertial frames, and second, the velocity of light in empty space is a universal constant, the same for all observers.
Fight.
Newton uses Galilean transformation. Einstein deflects.
Why doesn't the Galilean transformation work?
So here are the Galilean transformations for an object moving with a velocity v in the x direction. These are shown as a set of coordinates and a matrix. Up until this point, this was how it's believed that measurements in different inertial systems were related. However, Einstein disproved this with his two postulates. We can prove that the Galilean transformation can definitely not be correct by imagining a light pulse emitted from the origin of S, which is also specified by the origin of S'. Remember, at both these points, t equals 0.
S' will be moving with relative velocity v in the x direction.
So consider the light pulse arriving at the point x0 on the inertial system S. The observer standing in S sees the light pulse travel with speed c, and the time of arrival is t equals x0 over c. So this is how the observer in S specifies the arrival event.
For the observer in S', the light pulse will have travelled the same distance minus the distance travelled by S', or x0 minus vt, but the time taken will be the same, so this is how the event is specified in S'.
This means that according to S', the speed at which the pulse travelled was this equation here. But x0 equals ct, so the speed of the pulse in S' is c minus v, which contradicts Einstein's postulate.
Einstein uses Lorentz transformation.
But what is the Lorentz transformation? A small break to explain. Let's modify the Galilean transformation so that the speed of light remains constant. We'll limit the modifications in two ways.
Firstly, the equations expressing the coordinates of one system in terms of another must be linear, as the two systems are inertial. So, for example, a body moving with uniform velocity in one system must have uniform velocity in the other. Secondly, the symmetry properties of space must be respected. Again, for example, an event that lies on the x-axis in S must also lie on the x-axis in S'. So here we're going to write a new linear equation for the coordinates. By symmetry, we must have alpha equals beta equals 0, as the event in S' has no y or z components, so nor can the event in S.
For the same reason, t' equals dx plus et.
Symmetry also tells us that we must have y' equals y and z' equals z. Therefore, the most general form of the transformation allowed by symmetry is shown below. And expressions for the coefficients can be found by thinking about the system. Firstly, imagine how the observer S sees the origin of S' moving. It moves along the x-axis with speed v, so if an event occurs at the origin of S', then the x and t specifying this event must satisfy x over t equals v. Therefore, plugging this into our equation for x', we can work out that b equals minus av.
The observer in S' sees the origin of S moving with velocity minus v. Remembering that the velocity is given by x' over t', and here x equals 0 by definition, we find that a equals e.
Next, we think about a light pulse emitted at time equals 0. It must travel at the speed of light in both frames. And using some simple algebra here, we can find an expression containing a. Next, we consider the same situation, but with the light pulse being emitted along the y-axis. This light pulse still must be travelling at c in both frames. Distance travelled by the pulse in S' is this equation here. So using again our simple equation for velocity equals distance over time, we can work out a equation for A, including only universally known constants. And we can substitute this into the other equations to solve for each coefficient. These are shown here and put into the actual coordinate equations become the Lorentz transformations. In relativistic physics, this quantity here occurs very frequently and is usually named gamma. And putting this into our previous equations, we have a more formal way of putting the Lorentz transformation.
You'll notice that for a small v, the Lorentz transformation reduces to the Galilean transformation.
Newton throws an apple.
You might think that since you are not moving anywhere near the speed of light, you can forget the Lorentz transformation in real life. Well, if you rely on sat-nav to get you anywhere, and we didn't tell the GPS satellites about the Lorentz transformation, you could find yourself walking into a tree.